Here we're going to use the variation method to calculate the energy of the electrons in a helium atom. You may recall that we tried to use the Schrodinger equation on the helium atom, but because of the electron-electron repulsion terms, it made the problem into a three-body problem and did not yield an analytic solution. So we have to use approximate methods to get those energies and the wave functions. We tried the perturbation method before. Here we're going to try the variation method. In particular, we're going to use the variation method to calculate the energy of the 1s2 state of the helium atom. That is, both electrons are 1s. And we're going to use as a trial wave function the hydrogen 1s wave function, and our variable parameter will be the charge seen by the electrons. To use the variation method, what one does is to calculate the trial energy expectation value using a trial wave function phi. We evaluate this integral, and if the wave function is not normalized, we have to divide by the normalization, essentially the square of the wave function. All right, and again, just to emphasize, phi is a trial wave function. And it's chosen so that you can easily do this integral, and that will give you a trial energy. And this trial wave function has in it some adjustable parameters, and you adjust those parameters so you get a minimum energy. And those collection of parameters that give you a minimum energy give you the best wave function and the best energy by the variation theorem. Now let's use as our trial wave function the product of two 1s electrons, or two 1s wave functions. Let's use the 1s for electron 1 and also the 1s for electron 2. So there's our trial wave function, and in this these wave functions will have a variable parameter. So let's take a look at what the wave functions look like. For the 1s, this is the hydrogen 1s. Here it is. These are the trial wave functions for the hydrogen 1s. N equal 1, L equals 0. That's 1s. M sub L, of course, has to only be equal to 0. So here it is. So let's write that down here. So the hydrogen 1s for H atom was equal to 1 over pi a cubed to the 1/2 e to the minus r over a. Now what we want to do is to use this as a trial wave function for not the hydrogen atom, but for an atom that has an adjustable charge. As we said, we're going to use the adjustable charge as a parameter. So here, instead of having a +1 or +2 charge, +1 for the hydrogen atom, +2 for the helium atom, we're going to have an adjustable charge. And so now we have an electron, and it'll see that adjustable charge rather than the full +1 or +2 charge for the hydrogen or helium. So we want an adjustable parameter. So what you do is the wave function using that adjustable parameter, that adjustable charge appears as z cubed over pi a cubed to the 1/2 e to the minus z r over a. So that's how you take the hydrogen atom wave function for 1s and you convert it into an adjustable charge. And this can be used no matter what the charge is. For example, if you have lithium 2+, you have that's a 1 electron system, but there the charge in the nucleus would be +3, so Z for that system will be 3. All right, so that's what we have. So now we can write the total wave function, our trial wave function, as the 1s for electron 1. So that will be Z cubed over pi a cubed raised to the 1/2 e to the minus z r1 over a. That's for electron 1. And then times the same thing here, z cubed over pi a cubed raised to the 1/2 e to the minus z r2 over a. This depends on the coordinates of electron 1. This depends on the coordinates of electron 2. We multiply these together and we get the trial wave function. And the idea, and now with that trial wave function, we get a trial energy, and we vary this parameter z until we get a minimum energy, and that'll give us the best energy, and with that value of z, this will give us the best wave function. So that's where we're going. Now the Hamiltonian for the helium atom, if you may recall, that was equal to, actually it's equal to minus h bar squared over 2 times the mass of the electron times del 1 squared minus 2 e squared over 4 pi epsilon naught r1. So these are coordinates of just electron 1, and they have a similar expression for electron 2. So these are the second derivatives with respect to electron 2, minus 2e squared over 4 pi epsilon naught r2, coordinates of electron 2, and then you have the electron repulsion term, e squared over 4 pi epsilon naught r12, distance between the two electrons. Now what you want to do, see, this has a charge z. Where did this 2 come from? That came from the fact that when you multiply the two charges together, the charge on the helium nucleus is +2, and the electron is a -1 charge, so you get that -2 there. But now we want to make this a variable. We just don't want it to be a 2 there. We want it to be a variable. So let's change that Hamiltonian into a different Hamiltonian, which has an adjustable charge, minus h squared bar over minus h bar squared over 2m del 1 squared. That's not changed. Minus z. So there's our adjustable parameter z. So it appears in the Hamiltonian also, e squared over 4 pi epsilon naught r1. And then again we have for the second electron h bar squared over 2m times del squared for electron 2 minus z e squared over 4 pi epsilon naught r2, making that z a variable parameter, plus e squared over 4 pi epsilon naught r12. But now we have to worry, because here we have z and it's not necessarily equal to 2. So we have to sort of add back that extra charge, and that extra charge was initially 2, but now you subtracted off z, so there's a term 2 minus z e squared over 4 pi epsilon naught r1. That term is there so because we want to have a total charge of -2, and we can't just change arbitrarily the charge in the helium nucleus. And then there's also another term because we only have z of a charge here, so we have to include additional 2 minus z charge on the helium nucleus. So 4 pi epsilon naught r2. There we go. So now we have everything in there. 1, 2, 3, 4, 5, 6, 7 terms in the Hamiltonian. Well, if we look at this term here, these two terms, it looks like, contain just the electron 1 coordinates, and also it looks like it's the exact same thing as a 1 electron, except instead of having a +1 or a +2 on the nuclear charge, we have a z. So let me rewrite that as some effective Hamiltonian for electron 1. Effective means instead of an integer you might have a fractional charge here. And similarly you can write this as an effective Hamiltonian for electron 2. And then you have these interaction terms here. I'll write those here. Minus z e squared over 4 pi epsilon naught r1 minus z e squared over 4 pi epsilon naught r2. I'm sorry, it's z minus 2 minus z. Okay. So we already put these terms in the effective Hamiltonian. So this would be minus 2 minus z, minus 2 minus z, e squared. Well, I guess I got that minus sign already there, so that's that. And then we have that electron-electron repulsion term. So e squared over 4 pi epsilon naught r12. All right, so now we have 5 terms in the Hamiltonian, and what that means is that you have 5 terms. You'll have 5 integrals you have to do here. Okay, so let's call these term 1, term 2, term 3, term 4, and term 5. All right, so let's just do a couple of these terms just to get a sense. We won't do the whole thing here, but we'll just do a couple of the terms to get a sense of what's happening. All right, let's do this first one. This is the effective Hamiltonian, so kinetic with potential energy, and the potential energy is with the charge z on the nucleus instead of a charge of 1 or 2. Okay, so let's do that integral, and let's assume it's normalized so we don't have to divide this by the normalization constant. So this is the effective Hamiltonian for electron 1. All right, so let's evaluate that integral. All right, well, let's see. We said that the trial wave function is a product of 2 wave functions, and let's switch to this notation here. So it'll be the psi1s for electron 1 and the psi1s for electron 2. So we substituted in what we have in there. And now we have an effective Hamiltonian for electron 1. And then we have the 1s, multiply again with 1s, and psi1s for electron 2. And we're integrating over some all space tau. Now this is an effective Hamiltonian only for coordinate 1. Coordinates of electron 1. So we can take the wave functions that depend only on electron 2 out. So this would be the integral of the electrons in the 1s orbital for electron 2, integrated from space. And then we have left here the electron for electron 1, coordinates electron 1, times this effective Hamiltonian for electron 1 times psi1s for electron 1 d tau. And we should take the complex conjugate here. Now, if these wave functions are normalized, this is just equal to 1. So we're left with this integral we have to evaluate. The effective for electron 1 times psi1s for electron 1 d tau. Now these are wave functions for the hydrogen atom, and this is the Hamiltonian for essentially the hydrogen atom but with an effective charge. So that means that this energy is minus the Rydberg times the effective charge squared. All right, this comes from solving the Schrodinger equation where you don't have a +1 charge like the hydrogen atom. You still have a 1 electron system, but the charge in the nucleus is Z. So that's that contribution. So that first contribution to the integral, work it out, it's just minus Z times the Rydberg. And now let's do the second. Maybe you can see automatically that when you do the same thing for the effective Hamiltonian for electron 2, you'll just get again minus Z squared times the Rydberg RH. Okay, let's do one more integral and then we'll quit. So let's do, say, this integral here, that integral. Okay, so okay, let's do integral number 3. So what we're going to evaluate is this trial wave function with this Hamiltonian minus 2 minus Z e squared over 4 pi epsilon naught R1, we'll do the coordinates of the first electron, times phi. Okay, so let's rewrite that as, again, we have psi1s for electron 1 star, psi1s for electron 2 star, and then this Hamiltonian minus 2 minus z e squared over 4 pi epsilon naught r1, just for electrons, 1 times psi 1s for electron 1, psi 1s for electron 2, integrated over our space d tau. And again, since the electron 2 since this only depends on electron 1, we could pull out the wave function for electron 2, depends only on coordinates for electron 2, 1s for electron 2, and psi 1s for electron 2, integrate over all space, and lo and behold, if these are normalized, that's equal to 1. And now we have the integral of psi 1s star for electron 1 times the Hamiltonian minus 2 minus z e squared over 4 pi epsilon naught r1 psi 1s for electron 1 d tau. Okay, so now we're making some progress, but this is a little different. Let's go ahead and try to evaluate this. Let's put in what these wave functions are, and we can pull this out as a constant. So this is minus 2 minus z. Those are constants, e over 4 pi epsilon naught. And now we're going to integrate. Let's substitute in what the wave function is there. That's z cubed over pi a cubed raised to the 1/2 e to the minus z r1 over a, and then here's this 1 over r1, and then we have again the wave function z cubed over pi a cubed raised to the 1/2 e to the minus z r1 divided by a. Okay, and integrated over some volume of d tau. All right, so let's take these constants out. We're getting a lot of constants out there, and so that's equal to, so what do we have, minus 2 minus z e squared over 4 pi epsilon naught, and this is multiplied by the z cubed over pi a cubed. So those are those constants. Go back here. Yeah, those are those constants. You multiply those together, that pulls out. Times the integral of, we have e, well, we can combine those. This is e to the z r1 over a, e to the z r1 over a. So that's e to the minus 2 z r1 over a, and then 1 over r1 d tau. Now we're going to make a change here. What is d tau in spherical coordinates? D tau, that's a volume element in space. That's r squared sine theta d phi d theta dr. So where does this come from, r squared sine theta? Well, if it's in Cartesian coordinates, you have dx, dy, dz, but then you got to translate into d theta, d phi, and dr. So when you do that, you get these things that tag along. So now let's take this, substitute for d tau. We have a triple integral. So let's put this over here. So the triple integral is we're going to integrate over r from 0 to infinity. We're going to integrate over theta from 0 to pi, and we're going to integrate over for phi from 0 to 2 pi. And the function we want to integrate is 1 over r, r1. So this is r1 theta 1. These are all subscripts 1, meaning for the electron 1. E to the minus 2z r1 over a, and then we have r1 squared sine theta d phi d theta dr. So d phi d phi. And note that this doesn't depend, the thing you're integrating on doesn't depend upon phi or theta. It just depends on r. So we can pull that out. So this is an integral from 0 to infinity of, and then note that the r, one of the r squared over r, that's just r. So it's just r e to the minus 2 z r, we'll call that r1, over a. And then we have the double integral from 0 to pi and 0 to 2 pi of sine theta d phi d theta. If you integrate this, what you get is 4 pi. So that's another constant we stick out here. And finally, we're left with this integral, and this is where we go to Wolfram alpha. If you integrate that, let me just go on the next page here. So that integral is from 0 to infinity of r1 e to the minus 2z r1 over a dr. And Wolfram alpha says that this is equal to a squared over 4z squared. All right, so let's put all that together. We have some constants here, we have some constants here, and we got that 4 pi. So let's write down those constants, those 4 sets of constants, that one, that one, that one, and the one that we just did, this one. So we have minus 2 minus z e squared over 4 pi epsilon naught. That's one set of constants. The other was, another set was z cubed over pi a cubed. This is the integral right here, times 4 pi times a squared over 4 z squared. All right, so look at these things that start to cancel out. That 4 goes away, the pi goes away. We got an a squared, z squared, so this is just equal to, the whole integral is equal to minus 2 minus z e squared over 4 pi epsilon naught, and this is just z over a. A lot of work for that. And finally, we'll do, so this is integral term 3, integral term 4, you'll get something, and 5, you'll get something else, and so on. But just let me go down to the bottom line here. So if we evaluate all 5 integrals and put them into the equation for the trial, the expectation value for the trial energy, remember we evaluated that as the trial wave function Hamiltonian trial wave function, and these were the 5 terms we got. We put all that in. We're going to ignore the normalization here. We get this interesting quantity. So we have z squared minus 27/8 z, all right, and then minus 2 times the Rydberg constant for the hydrogen atom. So all that work, and we get this real simple equation here. All right, so what we want to do now is to find the value of z, which minimizes the energy, and using that value of z, that will give us the best wave function and the best energy. All right, so let's take, how do we minimize a function? Well, we take the derivative with respect to what we want to minimize with. So this would be the derivative of the trial wave function, or the trial energy, with respect to z. Z, remember, was our adjustable parameter. Let's go ahead and do that. This will be the derivative of z squared minus 27/8. Where did that come from? Z times minus 2rh with respect to z. And these are total derivatives. There's only a function of one variable here, so we don't have to use partial derivatives. So if we take, and then we want to set that equal to 0, and the value of z, which sets that equal to 0, is the value that minimizes the energy with respect to z. We go ahead and do that, and this we get, let's see, with respect to z will be just 2z minus 27/8. And this is a constant which comes out, and you can get rid of that because it's equal to 0. Or solve this equation for z. Z is equal to 27/16. Huh, that's kind of weird. So this is the effective charge at the nucleus of the helium atom. All right, so what we said, our model was, here we have a +2 charge, and here we have an electron here, an electron here. And this electron is not seeing the full +2 charge because of the screening effects of this electron. In fact, this is seeing not 32/16 of a charge, but a reduced charge, 27/16 of a charge. And similarly with this one, this electron doesn't see the full +2 charge of the helium nucleus. It only sees 27/16 of it. All right, so now we put in for this value of Z up here, this value of Z, and then that's the value of Z that minimizes energy, so that's the best energy of the trial wave function, and we get this. So the energy of the trial wave function is minus 1.241 times 10 to the minus 17th. All right. Now the exact experimental value is minus 1.266 times 10 to the minus 17th. So if we compare this, we find, yes indeed, as we expected from the variation theorem, that the energy we get from the trial wave function is greater than that of the true wave function. This is a bigger number. It's a smaller negative number. Okay, so it looks like variation theory works for the helium atom, and we got what we expected. Something was greater than the true. Now, if we want to get a better wave function and better energy, what we do is try something else rather than this effective charge. And if that, after we go through the calculations and minimize the energy with respect to those parameters, and we got the lower energy, then that would mean that would be a better trial wave function. So you sort of monkey around with the trial wave functions, minimizing each one with respect to parameters, and the closer you get to the true energy with that trial wave function, the better the wave function is and the better the energy is. Okay, so that's it.